I am Goh Zee Xin, so I will do the demonstration of the project 2. So the first question in the project 2 is to perform FSM plus D and FSM D to the GCD calculator. So this one is the GCD calculator with FSM plus D. So here we can see I have one DU and one CU, and I have one top module. Inside here, we can see that the CU have 3 steps. So in step 0, start equal to 0. When start equal to 1, I will go to step 1. And when start equal to 0, I will continue at step 0. At step 1, when P equal to Q, I will go to step 2. And if P is not equal to Q, I will continue at step 1. At step 2, done will equal to 1. And if start equal to 1, I will remain at this step 2. And then if start equal to 0, I will go to step 0. So I will do the situation. This one is the test bench. GCD calculator is to calculate the greatest common divisor. So firstly, I will input when start equal to 0, so I will remain at the same state. So when start equal to 1, I will go to step 1. So I will go to step 1. It will calculate until it get the same value, which is P equal to Q. So when equal to 1, when EQ equal to 1, so done will get 1. And then I'm in step 2. Step 2, I will get the result and done equal to 1. So the greatest common multiple for 4 and 8 is 4. Next is 255. So I have 255 as input. When start equal to 1, I will go to step 1. And then I will do until I get the common divisor. So when I get EQ equal to 1, I will go to step 2. When I go to step 2, done will equal to 1. So I will get the result. So the greatest common divisor for 255 and 51 is 51. So this one is the FSM plus D. Next, we will proceed to the FSMD. So this one is the FSMD. I don't have CU and DU. I just have one module, which is the top module. So at here, I just only have 2 states, which is S1 and S0. At S1, I will do done equal to 0, and then I will input if start equal to 1, I will do until the step 1. I will go to step 1. And if S start equal to, so in S0, if start equal to 1, I will go to step 1. And if start equal to 0, I will remain at step 0. So in step 1, if P equal to Q, I will directly give done equal to 1. So I will jump back directly to step 0. And then if P is less than Q or P is equal to Q, I will continue at step 1 and do the computation. So at here, I will simulate it. The biggest difference between FSM plus D and FSMD is at here. At FSM plus D, I have 3 states, and in FSMD, I just have 2 states. Because I will directly give the done equal to 1 when P equal to Q in FSMD. But in FSM plus D, I will give the done equal to 1 at the next state. So at here, you can see that when reset equal to 0, start equal to 1, when start equal to 1, I will directly go from state 0 to state 1 and do my computation. Then, when the computation is done, when the P is equal to Q, I will directly give the done equal to 1 during the EQ equal to 1 instead of jump to the next state. And then I will directly back to state 0. So I will get less cycle than the FSMD. Next, we will proceed to the C3-2, which is perform the multiplier version 3. So in the multiplier version 3, when S0 equal to, when at S0, when start equal to 1, I will go to state 1. And when S0 equal to, and when start equal to 0, I will continue at state 0. And when S1, I will directly go to S2. At S2, if count equal to 3, I will go to S3. Else I will go to S1. At S3, if start equal to 0, I will go to S0. Else I will continue at S3. In the RTL FSM chart provided, we can see that the count equal to count plus 1 is at shift 2, step 2. But I will put it at step 1 because it is impossible for us if we are using FSM plus D and we want to get directly see count equal to 8 after count equal to count plus 1 in the same state. So I will put the count equal to count plus 1 at step 1. So we can directly get count equal to 8 and trigger to step 3 instead of it shift too many times. So I will simulate the output. And this one is the test bench, and I'm using the S dot and Y dot to get output. So for us to easy to see the output, I change all the hexadecimal to decimal. So as we can see, 2 multiplied by 5, we'll get 10. And then we're equal to 1. And then 4 equal to 2, so 4 minus, and then 4 multiplied with 2, we'll get 8. And then that equal to 1. 3 minus 9, we'll get 27. So that equal to 1. 1 minus with 7, we'll get 7. So that equal to 1. And 136 multiplied with 137, we'll get 1x632. Then 10 multiplied with 15, we'll get 150. So from the result of them, we can say that the multiplier version 3 is functioned correctly. And this one is, we can see that when CNT equal to 8, I will directly go to state 3 instead of the inside the RTL ASM chart. I might need to go back again and then add the count again, because I cannot save the value and do the if else loop at the same state straight after I add count equal to count plus 1. Next, I will do the presentation of the P6 to P6-6 because I am choosing P6-6 as my one of the problem. So the P6-6 is the theorem Pythagorean addition. So this one is my DU and this one is my CU. So inside the RTL ASM chart given, the step 1 is nothing, and state 2 is doing the done and the note the P and note the Q with the maximum and minimum of the absolute. And then state 3 is doing the nothing and compare when if Q larger than 0. And then in step 4, which is I will do the scheduling. So I will separate for the multiplier and the addition. So I can just using one multiply divide unit and one addition subtraction unit. So in my code, I will doing the first one is I will select the division. I will do the divider and then go to the next state. I will do the square root of it. And then the next state, I will do 4 plus R. Then I will do R over 4 plus R to get S. Next, I will, and inside this, I will also shift the S with 2. I will shift, and at step 5, I will also shift the S by 1 bit to get 2 multiply with S. Then at step 6, I will do S multiply with T. And then at step 6, I will do the result of step 5 multiply with P. Next, I will add, at step 1, I will add the result from S6 with P. Then at S8, I will do the multiplication of S multiplied with T. So I will get the result of Q. Then at step 9, I will give done equal to 1. And then I will choose the P result at the selector. So when at step 9, when start equal to 1, I will go back to state 9. And if start equal to 0, I will back to S0 and start a new cycle. So at here, we can simulate it. In theoretically, when x equal to 6, y equal to 10, the result of output will get 10. Because this one is integer, we are unable to do the decimal. So the output P will always be the largest value between x and y. So if x is larger than y, so the output P will be x. And if y is larger than x, so the output will be the value of y. So at here we can see it is able to handle the negative value when I put negative x equal to negative 300 and y equal to 400. So x will equal to 65236 as negative 300 and y equal to 400. And I will get the result of 400 as just now I say. We will get the largest value. So 400 is the answer. So from the design, it can be said that the design is performed correctly and meet the requirement. And that's all for the demonstration video for project 2. Thank you.